All right. So thank you everyone for being here. So it's a great pleasure to introduce Mattia Libralato as the speaker of today. So Mattia got his PhD in Padua with Gianpaolo Piotta as a supervisor and Rolli Bedin and Andrea Bellini. And then after 1 year in Padua, he moved to Baltimore, where he worked for HST for 3 years, or maybe more, 3.5, and then moved on the JWST side. But he has just recently come back to Padua with the INAF fellowship, right? So today, every one of us is used to go on the Gaia Clive, click download, take proper motion right ascension and proper motion declination, and it's done. But before Gaia, and very likely after Gaia, whenever you want the best proper motions ever, you go to a couple of people in the world, and Mattia is one of them. And so I'll show you why now.
Yeah, thanks. Even too kind probably for my usual likeness. Yeah, hi everyone, and thanks for being here. And as you can see from the talk of this presentation today, we are going to discuss a few results that we got thanks to HST in the context of the internal kinematics of globular clusters. Let's see if it works.
Please click here.
Yeah.
Also, try again.
Okay, let's see. Yep, okay. So till a few decades or so, I would say, we thought that we knew everything there was to know about globular clusters and that we could simply represent them as a series of approximations. Globular clusters are spherical systems that lack of ordered motions. So stars just buzz around like bees in a beehive. Globular clusters are kinematically isotropic, which means that if you take two orthogonal directions of the motions and you study the velocity of the stars, it's the same. Globular clusters are collisional systems, so stars exchange energy with each other, and after a long time, they reach a complete state of energy repartition. Stars have the same average kinetic energy, and there is a very famous relation between velocity dispersion and mass of the stars. And of course, globular clusters host a simple stellar population, so stars born at the same time from the same molecular cloud, so they share the same chemical composition. But we do now know that this is an outdated view of globular clusters, and they are much more complex than these. Okay, almost all of them are spherical. They can rotate in the plane of the sky or along the line of sight. They can present kinematic anisotropies in their stars, and even after many relaxation times, they reach only a partial state of energy repartition. And of course, one of the most astonishing results is the globular clusters host multiple stellar populations, so stars with the different chemical compositions in them. The bottom line is that the more we study this system, the more puzzling they become. And even if these are among the most studied objects in astronomy, there are still a lot of open questions that range from their formation and evolution. That's too much. I spoiled. The formation and evolution, the way with which they interact with the surrounding galaxy, and how this interaction manifests to us. And this is true both for the classes as a whole and in the context of the multiple stellar populations. Since their discovery, we have a lot of theories. None of them seems to completely capture all the observational pieces of evidence that we have gathered. So there's still a lot of questions. And there are many other astrophysical topics that would benefit just by studying globular clusters. So one of the most debated is the existence of intermediate mass black holes in their core. The majority of what we know about globular clusters comes from photometric spectroscopy, mainly. And only recently, we started also to turn to astrometry as a new way in which we look at these clusters. And one of the main reasons is that before we didn't have the tools or the data set to do this kind of measurement of the internal motions of globular clusters. So astrometry, the study of the kinematics, can be a new way with which we can start to look for new pieces of information that can help us to link all the different topics for which we have still a lot of questions. For myself, at least, probably all people that, like me, like to work on the kinematics of globular clusters, the ultimate goal is to have a 3D representation of globular clusters. So you need to put together line of sight velocities and motions in the plane of the sky, so proper motions. There are pros and cons of using either one of the two techniques. I mainly work with proper motions. one of the things that I love about proper motions is that they provide you two directions of the motion at once. So you can measure directly anisotropies in the kinematics, and these comes in handy when, especially when you do modeling, and also you will see they give you a lot of useful insight. Nowadays we have HST and Gaia primarily as sources of high precision proper motions. We started also to have JWST data to do this kind of measurements, but the JWST based only works are still a little earlier in the mission, in the life of the mission. And I work mainly with HST, so today you're going to listen to basically almost all things with HST. Before we move to the scientific part of the talk, I usually like to spend just one slide to stress that computing proper motion in general is to study the kinematics of stars in clusters or whatever. It is extremely complicated. This is true both for Gaia and for HST. One of the additional layers of complexity of computing proper motion with HST is that HST is not an astrometric mission. It's not designed with the sole purpose of computing proper motions. So when you have to compute proper motion with HST data, the job makes you link heterogeneous data sets that were not even designed with astrometry in mind for completely different scientific purposes to get your homogeneous product, which is the proper motion catalog. And with heterogeneous, I mean data set taken with the different cameras on board of HST, filters, exposure times, number of images at disposal, temporal baselines at disposal, orientations, and so on. So within the same field of view, there can be extremely complex to assess the quality of your data sets. So a lot of work that is done behind the scenes is spent to get the best astrometric and photometric quality as possible from each of the images that you have, how to link them together to get the best proper motions, understand them, understand the systematics that offend, mitigate them, so that you can actually study the internal motions of the stars. Just to give you a flavor of what does it mean a heterogeneous data set. Here on the right, there is this plot. On the y-axis, there is the proper motion error of the stars as function of magnitude. This is taken from a catalog that we published a couple of years ago. And the points are color-coded just by the number of images that were used to compute the proper motions. And even if you're not familiar with proper motion, you see the plot, there are a lot of colors, a lot of trends. So at any given magnitude, the stars can be measured with 10 microsecond precision per year precision or 10 times worse. So part of the job is to understand which stars to trust when you do the proper motions and so on. But at the end of the day, when everything is done, you can see here that you can achieve very high precisions. We can measure stars even at better than 10 microseconds per year, something comparable with Gaia as well. And when I started back in the days to do this research, one of the examples I was given to explain what does it mean 10 microseconds per year was that there's a precision that will allow you to see a human hair growing on the head of a person standing on the moon from the Earth. So it's an extremely tiny measurement that you can make thanks to proper motions. If you're interested in looking at the technical details or just using one of the latest collection of proper motion catalogs, I refer to our paper that we published a couple of 2 years ago now. Yes, the code name is HACS. This is a collection of proper motion catalogs for 56 globular and 1 open clusters that were the target of a very famous treasure survey with HST. And this represents the most complete and homogeneous collection of proper motions that you can have for stars in the core of globular clusters today, which expand and complement what you have from Gaia, but the crowded regions in the core of globular clusters that are usually avoided with Gaia, and to stars fainter than the Gaia limit. And I will show you later in this presentation what this means. Okay, so once you have your proper motions, you can do multiple things. Here I listed just a few of them, the most basic one. You can infer the cluster membership. So you have an object in the field, and you try to see if it is a member of the cluster, if it is stars, or member of another system. You can measure the absolute motion of globular clusters, for example. And this is how the absolute motions in the plane of the sky were computed before Gaia came to help us. And now this task has been mainly superseded by the Gaia proper motions. But there are still a few objects where Gaia struggles for which HST can still be one of the few resources that you have. Three things that you can also do thanks to proper motions that are also three things that give you some of the ingredients that are usually needed when you want to make this recipe of globular clusters are the systemic rotation curve in the plane of the sky, the velocity dispersion profile, and the so-called anisotropy profile, and the measurement of the level of energy prepartition of globular clusters. And today I will go through these three topics. The first two will give you just a very brief overview, and I will mainly focus on the latter one, which is one of the newest things that we started to do thanks to proper motions. So let's start from the systemic rotation. Most of the rotational curve in the plane of the sky for globular clusters we have today are made using Gaia proper motions. And the main reason is that with HST, it is with the techniques that we use to compute proper motion with HST, the systemic rotation component is actually removed from the proper motion themselves. It's part of the process. It takes some time to explain, but if anyone is interested, I can explain that. But it is not completely lost, at least for all clusters. It can still be retrieved and with some work. And it is how back in the days before Gaia arrived, how proper motions the based rotation curves were computed for globular clusters, 47 TAC, and NGC362, and so on. Since we started to see that globular clusters rotate also in the plane of the sky, we started to make the curves. We have seen that clusters basically can show you two different types of curves. There's clusters like the one on top, 47 TAC, clearly show that there is a rotation pattern. So here on the x-axis, you have the distance from the center of the cluster, and on the y-axis, you have the tangential component of the proper motion, which is the rotation. And I choose this cluster not by chance, not even the paper, just because it is one of the few where you can see one on top of the other, the measurement with Gaia and HST, just to say that it was possible to compute proper motions and rotational curve also with HST. If you focus on this plot on the top, you see there are multiple things. There is an increasing part in the innermost regions that increases like a solid body. Then you have a peak in intermediate regions, and then it starts to slowly decrease going further from the center. And all these features that I've just described are important pieces of evidence that give you that let you understand, for example, what is the role of the angular momentum in the clustering supporting it. Well, how the cluster formed and how important was also at the formation, the rotation in the cluster, the interaction that it might have with the surrounding galaxy that is expected according to the theory to shape the rotational curve probably here very, very far from the center and the edges. And also it can give you a hint of the dynamical status of the cluster. If there are peculiar substructures that can create some peculiar kinematic features, because if, for example, if there is a substructure that rotates extremely fast, you might be able to see a kinematic anisotropy in the stars. So again, putting all the different pieces together, you can properly interpret what you see. And so again, this is extremely useful for the modeling and also give you some direct insight about globular clusters and what their dynamical life. But not all clusters show such a nice rotational curve. There are others like the one at the bottom, NGC362, that instead shows something very different, which is a flat curve. And this can be due to two reasons. The first one is just a projection effect. If you see that the cluster is rotating mainly along the line of sight, so it is seen as John, you cannot detect motion in the plane of the sky. So there's no curve. But it is useful to know because it gives you an idea of what is the inclination of the axis. And the other explanation could be simply that the cluster is dynamically odd. Over time, this curve on top changes. The clusters, the stars interact with each other, and they are lost, so the angular momentum decreases, the rotation decreases, and this curve flattens out. And this is probably what happened for NGC362, because we know from line of sight that it is not rotating fast either along with the radial velocity. So it means that probably this guy is in an advanced stage of its dynamical evolution. So again, this is a very brief overview. Just wanted to highlight that the systemic rotation curve is a very important piece of information that we can use. It can give you directly hints about dynamical status just looking at it. ordinary about the configuration of the system, and something that is useful then to have in handy with the modeling. Model can be done with or without considering rotation. Knowing this, then it allows you to make less assumptions when you do it off the bat. And there are people that spend most of their career just on this specific topic of the kinematics. The second ingredient I would like to show.
Mattia, can I ask?
Sure.
Just to curiosity. So have you ever tried to compare the proper motion results for NGC362 with Gaia? That's the first curiosity. And the second, so do you have an idea about how many clusters in the AX survey are, you can get velocity, rotational velocities? So basically you have references that are good enough to get the rotation.
So for the first question, I believe so there were a lot of papers like the Basile, the Baumgart, and so on collection. And I believe that NGC362 was not one that showed the rotational curve also with Gaia. So for the second question is, as you have seen, I choose these two clusters here. They're not by chance. It's because one of the ways to retrieve the systemic rotation component is to have another reference group in the background to use to reconstruct the rotational curve. And these two have both the SMC. So that is the one way is to search for some of the clusters that have SMC, the Sagittarius, Davide, and so on. But there are also other ways to do that. And there was a recent paper by Maximilian Heberle. He made the proper motion catalog for omega sen, and he combined it with Gaia. And so he made the relative proper motions as we do, so he lost the rotation component. But by comparing logically the proper motion of his HST proper motions with the Gaia ones for the stars in common, he was able to reconstruct the rotational curve in the innermost region of the omega sen, which are usually not even tried with Gaia. And he showed that the models that are from the Baumgart database, so that to give you a name, are just overestimating the expected rotation there because they are extrapolated from the flight radius or whatever. So there are multiple ways to do that, not only with those that have someone in the background. You can also use Gaia, but of course, it depends on how many stars Gaia has there. Okay, so going back, velocity dispersion and kinematic anisotropy is the second ingredient that we can get. Here I try to sketch let's say, the anisotropy profile that we expect to see for some clusters with the proper motions, which is something that we might expect according to how the cluster have formed, the subsequent evolution, interaction with the surrounding galaxy, and which has been partially, at least, probed also with observations by HST and Gaia. So here you have, again, distance from the center on the x-axis, and on the y you have this ratio between the tangential and the radial components of the velocity dispersion. Tangential and radial, the two orthogonal direction of the motions that are used to compute the anisotropies with proper motions. And radial is always in the plane of the sky. So in the direction that passes through the center of the cluster by inward or outward, but in the plane of the sky. So there's no line of sight measurement here. This is just proper motion based. And you see this value here, if it is 1, means that the two components are equal, so isotropy greater than 1, tangential anisotropy, lower than 1, radial anisotropy. One of the things that, you see there is a very specific pattern, and that can be the result of the formation and evolution of the system. So, say if the cluster forms compact after the Biot relaxation phase, then it expands. This expansion phase, the stars tends to move preferentially outward radially. So they are imprinted in the radial anisotropy in the kinematics. But depending on the area that you are in the cluster, this radial anisotropy is not, doesn't last forever. So for example, in the core, as you can see here, the core is isotropic. This radial anisotropy has been removed efficiently by two-body encounters. The stars exchange energy, they lose memory of what they were doing before, and after a while, everything is isotropic. Then you see the radial anisotropy start to increase because there is a compromise between the isotropic process and the primordial anisotropy. It reaches a peak, and then it starts to decrease again. And these, where the stars will become isotropic or even slightly tangentially anisotropic. And this is due to the interaction with the surrounding galaxy. When you are very far from the center, the cluster feels the most the tidal field of the host galaxy. And this, so the host galaxy tends to strip stars from the clusters, and this selection is somehow this process is selective. It tends to strip more easily those stars that are already moving radially outwards, so those that actually carry the anisotropy in the kinematics. So after you remove them, what is left are isotropic or tangential isotropic ones. And so this is what some works, theoretical works suggest to us. And thanks to HST and Gaia, we were able to probe at least partially this. We were able to see the isotropic region, the radial isotropic region for some clusters. What is still an uncharted territory is the edges of the cluster. With HST, it's not even feasible to ask time to get this kind of measurement. Gaia technically has the post-Gaia disposal, but because of in the cluster there is mass segregation, in the outskirts you expect to see mainly faint stars, low mass faint stars. And for the majority of clusters, these are out of Gaia's reach because Gaia focuses on bright members. And even if for close by systems, you can go a bit down the main sequence, then you have the proper motion error start to increase. So the effects here are going to expect it to be very tiny. So measurements are uncertainty and so on. And also membership becomes problematic, especially when you are observing clusters toward the galactic plane in the direction of the badge. You have a few members in a galore of field objects. So understand who's who is complicated. So this is why, for now, at least, this is just according to the theory, the speech. Here I forgot, I put a question mark in the centermost part of the cluster. I said that clusters are isotropic in their core. True, there can be things that change that isotropic field. Presence of intermassive black hole, the collapse, other peculiar substructures, they can imprint some anisotropies. So again, as I said, when I was talking about rotation, before interpreting any result, one would like to put all the different pieces together to get the complete picture and understand what's going on here. With HST and Gaia, as I said, we've seen these for many clusters, different features. Recently with HAX, we have this large collection of proper motions. We also started to study some general properties of kinematic properties, globular classes, in a similar fashion to what has been done historically for photometry and spectroscopy, put all the classes together to see that things that are common. And one of the things that we were able to do was to see the, let's say, temporal variation of these plots. So we took our classes and we divided them in classes that are dynamically young. So stars have experienced only a few relaxation times, so they might still be able to show these kind of features. And dynamically old systems that instead, as stars experience a lot of relaxation times, so they've lost probably most of these features. And this is what we saw. So this is the anisotropy profile. Here you have the distance from the centering units of light radius for dynamically young systems. Yeah, the gray points are the individual measurement for all clusters, which were properly normalized, so they can be compared to this kind of plot. And the black points are just the running average or running median, you don't remember which one, of the gray points. And you see basically what I showed you before in the sketch. So you have an isotropic region here, and then there is a radial isotropy that starts kicking in. And the further you go, the stronger it is. Even at a few half-light radius, which is the edges of the HST field of view that we have. But when we move to dynamically older systems, this kind of anisotropy tends to disappear. Again, because this is in the core, so probably there's just the two-body encounter process that tends to erase the anisotropy. And so these stars are basically isotropic, and even at a few half-light radius from the center of the cluster. Again, this is a confirmation of the theory. Even too many slides. Okay. And again, so this is just a very brief overview that I wanted to give. Just looking at that anisotropy profile, you can have insight on what's going on. You have insight about some processes that happen when the cluster is formed. When we will be able to see very far from the center, we will be able to see how the classes interact with the surrounding galaxy and so on. Yeah?
Do you find any dependence on the position of the cluster in the molecular conceptual sense?
So where the tidal field is stronger versus.
So this is something that I haven't checked directly with this kind of general behavior, but I checked with in the context of the multi-populations. We found that you will see later that there can be some radial dependencies of some profile like this for the different populations, and they seem to be a bit dependent on where you are in the galaxy. But these, remember, are centermost regions, and those kind of effects are probably being stronger when you are very far from the center, right? So that was just a hint, let's say. Yeah. Okay. Let's see. Okay. Good. So the last ingredient I would like to discuss today a bit more in detail is this level of energy prepartition, and this is one of the topics that I like the most. It is one of the most challenging measurements that you can make with proper motions nowadays. It's also one of the few things that you can do only with HST and not with Gaia. And the main reason is that to assess the level of energy prepartition in a cluster, if you remember the introduction, you have to find the relation between the velocity dispersion of the stars and the mass. So to get a robust measurement of this relation, you want to probe a relatively large mass interval. So you need to probe stars along the main sequence, but as I said before, with Gaia, for the majority of clusters, this is not possible. So this is why with HST, you can have very deep images, you can go down to ideally the end of the main sequence. So this is something that you can do, and that has been done. So I like this topic because it makes HST shines in the Gaia era even now. So from the theoretical point of view, we already knew since many years ago that globular clusters are expected to just reach a partial state of energy prepartition because of the so-called Spitzer instability. So the innermost and the outermost region becomes decoupled, they do not talk to each other, and the stars do not evolve as you expected with the velocity dispersion and the mass, and so this is halted. So only a partial state. So the usual expression that is used to explain the energy prepartition and the relation is this one here: sigma velocity dispersion scales as the mass m to the minus eta, level of energy prepartition. 0 means no energy prepartition, 0.5 means complete energy prepartition. What has been shown by theoretical works is that eta never reaches 0.5, it's always below. This is one example. Trinity and van der Maal in 2013 has showed this variation of eta as function of time for different regions of the cluster. And you can see that this is the 0.5 threshold. Of course, these simulations this eta never reaches 0.5, is always well below. And also another thing you can see is that the pace with which this eta parameter changes as function of time. As function of time is different. And obviously, in the core, 2 mode encounters are more frequent. The energy prepartition develops faster. In the outskirts, it takes more time because it's more diffuse and so on. With HST, we have started to see this. If I remember, omega sen, probably one of the first measurements in 2 fields that showed that the energy prepartition was way below 0.5. One of the first detailed analysis that we had is always NGC362, one of the cluster. So here on the left, what you see is CMD, where I show all stars that are members of this cluster, which have a proper motion reliable enough to study the internal motion. And you can see the turnoff is about 1980.5. So we can go like 6 magnitudes below the main sequence turnoff with good proper motions. So what we did was to divide the main sequence into different equally populated beams. In each beam, measure the average velocity dispersion, magnitude, converted the magnitude to masses with an isochron. And then on the top right, you see this plot where you have in a log-log plane, the velocity dispersion is function of mass. We fit the point, the straight line. The slope is the measurement of the level of energy prepartition eta that we found to be 0.11. So this is an extremely dynamically old system we have discussed before, rotational curve, and also it is isotropic and various half-light radii. And also it has it has a level of energy prepartition which is way below the complete energy prepartition, still in a partial state. Another thing that we were able to see in this cluster was that eta actually, as predicted by the theory changes as function of distance, and this is shown here on the bottom right. So you have eta as function of distance, and you can see clearly that it goes from a value of 0.3, 0.4, and then down to less than 0.1 at more than 2.5 half-life radii from the center. So again, this confirms the prediction that we have from the theory: partial state of energy partition, different rate of evolution for eta as function of distance. And since then, we have started to look at more clusters. This is another one, 5904 and 5. I'm not going to go through the old panels again. Basically, the same results. Energy partition globally within the field of view is below 0.5. And locally, it changes and decreases the further you go. And there is another recent paper by Laura Watkins. She showed that for other clusters, level of energy partition always below 0.5. And if for clusters for which it was possible, there is a trend with the level of energy partition that decreases. As for the rotational curve, the anisotropy profile, and so on, so knowing the value of eta is useful in the modeling, gives you insights of the dynamical status and so on. But also can be used for more empirical applications, let's say. It has been used, for example, to infer the pre or a post-core collapse state of a globular cluster. And this is a nice theoretical work by Paolo Bianchini, where he basically showed that when you are far, different, depending on when you are in the collapse phase, very far away or in the collapse, the local and global level of energy partition are different. So when you are like very far from the collapse, the cluster both globally and locally behaves as it should. So like stars exchange energy, the high mass stars slow down, the low mass stars speed up, and the energy partition increases. But when you are reaching the collapse, things change. The locally stars exchange energy again, as we expect. But globally, you see that the high mass stars sunk toward the center because of the mass segregation there is in the cluster, which is accelerating because there is a collapse happening. So they increase the velocity. The low mass stars instead are thrown in the outskirts, where, as we know, the velocity dispersion decreases the further you go from the center. So they are expected to decrease the velocity dispersion. So basically, the energy partition globally is not increasing anymore. It's actually going the other way around. So Paolo Bianchini proposed this in this work. Is this kinematic concentration parameter. It is the ratio between the level of energy partition measured locally, like at the half-life radius, and globally, so within the entire half-life radius. And in this plot, this is this concentration parameters function of time. Here, you see MEQ instead of eta. It comes from a different formulation of the relation between velocity dispersion and mass for energy partition, which is mass dependent. The ones that I showed you before has one value of eta for all masses, but it has been shown that that is a good approximation for relatively large, for small interval mass intervals. When you have a very large one, you might have to take into account that there is a dependency on the mass. And so this is something that, of course, you can measure as we did before, not with a straight line with a different equation, but it is doable. And this is what we did for NGC362. So here in this plot, you see this CK parameter as it changes. The collapse happens here at 8 gigayears, where there is this vertical line. So you see this parameter is always constant, almost constant and below 1. When the collapse starts, it increases, reaches a peak, and then decreases a bit and stabilizes, oscillating a bit. So we measure this for NGC362 and found this point right here. So according to this age and its kinematic properties, we infer that is in a post-core collapse phase of its life. And we already knew this from surface brightness profile, but this is the first time it has been done using kinematics. It is a very useful tool to try to infer this kind of status of clusters, which should overcome some of the limitation that you have when you use like surface brightness profiles and so on. So this is basically about what I wanted to show for the kinematics of globular clusters as a whole. And now that we have started to increase our knowledge from the observational point of view, this, of course, has made the theoretical side of the framework to improve. So now, for all the different features that I've shown, we have started to look at even more complex or peculiar features to look at. One of the recent things is to look at the energy partition. Instead of using the average velocity dispersion of the stars, divide it into each of the two components of the motion, because it might have a different rate depending on how the cluster rotates, formatted, anisotropies, and so on. So it's very complex, but I wanted just to give you a simple overview. And the last thing that I'd like to show you is the same thing that I discussed, but in the context of the multiple stellar populations, which is something new that we've started to look at thanks to proper motions. And for those of you that are not very familiar with the phenomenon of the multiple populations, we want to, let's say, summarize it in the two sentences. You can think that in clusters there are two major groups, let's say, of stars. There are stars that have a chemical composition typical of the primordial class from which they form. They are called first generation, first population, whatever you believe. And then there are second groups of stars that, with respect to the first generation, are enhanced or depleted in light elements, depending which one you look at. They can be helium enhanced, they can be iron richer, they can have other chemical peculiarities, and these are called second generation population, whatever. And this is very puzzling phenomenon. It is ubiquitous. Almost all galactic globular clusters studied with the proper tools show the presence of multiple populations. It is various. No two globular clusters are alike. This is a collection of CMDs made with the same filters and colors, but different clusters. And you see that all of them show that there are multiple sequences in these CMDs, which are related to the different populations that you have. But the complexity of the different sequences is different from cluster to cluster, which is the variety I was talking about. So this is one very peculiar phenomenon that we're discovering globular clusters, very puzzling. It has been extensively analyzed with photometry and spectroscopy. Many different theories have been developed, and all of them basically fail one way or another to explain why we do see these different populations. And recently, there have been a couple of works, theoretical works, that started to suggest that looking at the kinematics of the multi-population might be something new, and something that can provide us new constraints and new ingredients in these recipes that we are trying to make about the phenomenon of the multi-pops. There are some theoretical works that say that you can even discern between which formation scenario mechanism actually created the peculiar chemistry in the second generation stars, looking at the rotational curve of the velocity dispersion. There are other works instead that say that this is not possible, of course, very good. Regardless of the formation mechanism itself, most of these theoretical works seems to agree that the second generation stars form more spatially concentrated than the third generation stars. And then they start to diffuse outward radially. And if you remember before, this means that they should have imprinted in their kinematics and anisotropy, a radial anisotropy. So measuring the velocity dispersion and anisotropy profile can first verify if this condition is true, and also help you to understand a bit more what was the initial configuration, and say something to plug into your modeling. So the bottom line is velocity dispersion, rotation, energy partition, all useful tools with which we can learn more about the first and second generation stars in globular clusters. And we have started to look at this first with HST, again, then with Gaia. Gaia has some issues, limitations, not issues, which is that it is difficult to disentangle multiple populations using just the Gaia filters, right? For those that work in this topic. So sometimes you need to use an auxiliary catalog that have, like Stefan catalogs, that have photometry suitable filters that are more sensitive to the different chemical composition of the stars, UV, those kind of things. In HST instead, for the majority of the galactic globular clusters, we already have observations from the UV to the near infrared. So there's a lot of things. And this way we can easily target different populations and then study the kinematics. One of the things that we start to see is, of course, that the time works against us. So dynamical processes erases all the fingerprints of the differences in the kinematics and the structural properties of the populations. So if you look at the core of clusters, you might not see anything. The further you go, the stronger these differences might still be, and so on. So this is why it's still something that is relatively new, because with HST, the majority of the data set that we have are in the core. So this kind of features might be seen at the edges of the fingerprint. Recently, we started to do basically the same thing that we started to do historically for the globular cluster as a whole. We started from analysis of a few clusters here and there, and then with the more observations that we had, the more analysis we can do. And now we started to do general analysis of the kinematics of the different populations, putting everything together, similar to what has been done for the photometry, for example. So this is what we did with HACS. So we took all the clusters that we had at disposal. We focused on the red giant branch stars, where the tagging of the multi-population is more straightforward. We took all their position, the stars of all these, the position and proper motion of the stars. We normalized them, so to be collected as if they were part of just a big globular cluster. And then we studied the velocity dispersion of the stars of the first and the second generation stars separately. And this is the result. So I know there's a lot of panels, but I will break it down each. So to start here from the left, you have the usual anisotropy profile that I showed multiple times. And on the top, you have the result for the first generation stars in yellow, middle row, second generation stars in blue, and at the bottom, just the average trends that we fit to the point above for a direct comparison. And what you can see is that first generation stars are basically isotropic with just a very mild radial anisotropy at a few half-light radius from the center of the cluster. But the second generation stars are much more radial anisotropic than the first generation stars. And this seems to be a general property of the populations. And this seems to agree with the theoretical predictions of second generation stars form spatially concentrated, they start to diffuse outwards, and so they have a stronger radial anisotropy with respect to the first generation stars, and instead are more diffused and have more time to remove this anisotropy. And we also analyzed each of the two components separately of the motion. Here, the middle column is the radial velocity dispersion profile, and on the right is the tangential velocity dispersion profile. And what we found is that the second generation stars are kinematically colder at the lower velocity dispersion, because they have a difference with respect to the first generation star, the tangential component, because again, they are primarily moving in a radial direction. So the one that is affected the most is the tangential component. It is again confirms some of the theoretical predictions. And in this work, we also see that they are both qualitatively and also quantitatively in agreement with the expectation. These features are not extremely strong, as you can see, because again, we are in those center of region. They start to become important when you are at the few half-light region from the center. But it is, in my opinion, a promising result because it shows that we have the tools to do this kind of things. We should continue to investigate the phenomenon even further, find for the center, so that we can get a useful insights also on this phenomenon from a kinematic point of view. And I've basically completed my presentation. I will try to wrap up, but I thought that the better way to do it just with respect to the outline was to look at the future. What can we do, the next steps with the current and future facilities for globular clusters? And so I wrote down my to-do list. If you start from the core of globular clusters, one of the things that which is the one that we have more analyzed, we need to complete the kinematic picture. One of the things that lacks the most is an estimate of the level of energy partition for a large sample of clusters. And also start to look at very peculiar structures that are in the core. There are recent works that show that there can be subclusters of stellar mass black holes or neutron stars in the core of some clusters. Or to also search for intermediate mass black holes. It's one of the most debated topics in astronomy, and Bologna knows this somehow. And to do this, we can, for some clusters, still use HST. We might wait for other clusters to use detectors on ELTs, activity with the AO, but it might be still a challenging measurement because there can be some things that make it difficult. And I usually move on to the next part of the to-do list, but I cannot not mention the recent result that we got in the context of the intermediate mass black holes, because this is a very cool result that was recently found by Maximilian Heberle, who's a PhD student in Heidelberg. And he is analyzing the globular cluster Omega Centauri. He had, using HST data, global Omega Cen has a lot of data set over more than 20 years, because it is used also for calibration of the instruments of HST. So he made this exquisite proper motion catalog, and while he was analyzing it, he found in the centermost arc second of the cluster, not one, but even 7 stars that is moving faster than the escape velocity that we expect in that region of the system. And one of the explanations that we think is what makes them to move this fast is that there is a very massive unseen object there, which can be an intermediate mass black hole. When I say fast, these stars means that really move fast. But this is just one of them. Taking different snapshots over time, you can clearly see that the stars moved by several pixels. For those of you that do not work on these topics, when we study internal kinematics of globular clusters, usually stars move by fraction of pixels, just as a reference. So the fact that this one moves that fast is proxy that is really a bullet. But this might be the smoking gun that we were searching for a long time for globular clusters. And also, I think last week, or even this week, there was another paper for now on M15. They found an hypervelocity stars that was moving close by, and they backtraced the orbit of it, and they found that it was coming from this cluster, according to some model of the orbit. So that could be the second proof that there is another intermediate mass black hole over there that has thrown away an object. So there's still a lot of work to be done for this. The mass, the lower limit of the mass for the intermediate mass black hole in Omega Cen that we found was of the order of 8,000 solar masses. And that's the need of line of sight velocities. There's still more work, but I believe this is a very encouraging result, because after a lot of debate results, finding something this straightforward is very encouraging. And so probably it will hope to reboost this specific part of the research field in the future. If we go back to the to-do list and we focus on these regions just outside the core, at a few flight radius from the center of the cluster, where we still have to do a lot of work because we do not have a lot of data set. We are trying to get them. And these are key regions because are those where we expect to see the peak of the rotational curve, the peak of the radial anisotropy, and so on. So the relaxation time is longer, so differences in the kinematics of the multiplox can still be perceived. So it's a very important region to be analyzed. And to do this, we can still use HST, Gaia. Probably JWST is going to be the game changer because, as I said before during the talk, in this, the further you go, the more numerous stars are less massive than in the centermost region. So they're less massive, they're faint, they're red, so they're brighter at long wavelength. And JWST primarily works on near infrared and also mid infrared, but for the things that I care, this is near. And with JWST, so might be better suited to this analysis. And within the first year or so, we already showed out of the bat that we can measure proper motions using JWST. For now, in combination with HST or Gaia. And we did this with NIRCam, with NIRIS, and with MIRI here at the bottom. We did all of them. We had the tools to do this right after the data became public available. And these are all motions of the LMC. So we were able to resolve the kinematics of the stars in the LMC now, because also we have a longer temperature. And then what is left is to basically study all the outskirts of the clusters. This is an uncharted territory, as I said before, that can be informative about the interaction that the clusters have with the surrounding galaxy. So it's very important to look at these regions. Gaia has limitations. Gaia near might be better suited if we will have it. And probably Roman, the former W first, can be game changer because it will have a wide field of view like those of ground-based telescope, but the resolution of a space-based one. And that's basically it. I think that I bothered you that much. But it's moving very slowly. Okay, very, very choppy, but never mind. Thank you for the attention.